downward continuation. If you remember, when we solved this all these boundary value problems, our first assumption was that the data are at the boundary value, but at the boundary. So what is the boundary? So we have sea level, the surface of the spherical Earth, and this is topography. Our main assumption for solving boundary value problem is that our data are at sea level. So all these Stokes formula or determination methods, whatever that you have done so far, are based on this assumption that the sea level is the boundary. However, in practice, these data are not at sea level. They are at the surface of the topography or the surface of the Earth. Then this is not the situation that we expect actually. So we want to have the data down here, but we have the data up. Also, we always assume that outside the boundary, we do not have any mass. But here we observe that we have topographic masses between this boundary and the surface of the Earth. Now, in this section, I will discuss just how to bring down this data to the surface of the boundary. And later we will come with the topographic effect. How to program it. So downward continuation means to compute the data or bring data to boundary. That's me. So how do we do that? Let me start with the equation of the gravity or spherical harmonic expansion of the gravity anomaly. If you remember, it was 1 over r summation n 0, 0, 2, doesn't matter, n minus 1 r n plus 2 Tn. Tn is the disturbing potential. At sea level, and it is the gravity anomaly at r. This is the geocentric distance outside of any point outside the Earth's surface. So if I consider Tn, n minus 1 and r together, simply I can write delta G at the level R will be summation from 2 up to infinity. Oh, there's no minus here, sorry. And it will be R n plus 2 delta Gn. Why? Because we already know that at the surface of the sphere, Laplace harmonics of the gravity anomaly has this relation with the disturbing potential. So now I already know that delta G is 2m plus 1 4 pi integral delta G Pn cosine. Therefore, I come to a formula which is this. It will be 1 over 4 pi integral 2n plus 1 r over r n plus 2. Oh, I missed the summation. So Pn cosine psi delta G at integration. That's the formula which, if you have this delta G at the surface of the boundary, this one, you can generate that delta G at any surface outside, any point outside the Earth. So, one way to determine the gravity anomaly at the surface of the boundary from the surface of the Earth is to use gradient approach. How is it? So how can we do that? So I need to take the derivative of the gravity to compute this Taylor expansion. Let's see. I say that the gravity at the surface should be gravity down, for example. Should be gravity at the surface plus derivative of this is h multiplied by h. So this is a linear function. So I need to just compute the gradient of the gravity, the radial derivative of it, and this gradient is multiplied by h, and we'll add it to the surface gravity because it should get larger when it goes down. So then you come to the gravity at the surface. The problem here is just to compute this derivative. This value is given at the surface, and this one is at the boundary. H, the height we need to know. So what do? I take the radial derivative with respect to r, radial of this function, simply. So how do we do that? Okay, I will write, okay, derivative of this will be 1 over 4 pi summation. Okay. If I take to another derivative, m plus 2 divided by r, 1 minus comes here, r over r n plus 3 pn cosine delta G dc. That's one way. Then I can compute the gravity, the derivative of gravity anomaly, and just add it. But the problem is that this gravity is down at this already at sea level. Then it is actually it's a problem because we want the derivative of the gravity anomaly from the sea level, but it is also already down. One way to solve this problem is to do another remove restore technique to a little bit simplify this. Remove restore technique. So I will remove the gravity, the effect of gravity. Not here, it's not here. And then you need to compute just this derivative from it and add it to the gravity. But this gravity this derivative can be computed to like this. That the derivative of this is actually the derivative is the this should be R2 over 4 pi integral of delta G minus delta G. P is the computation point, L03, and the sigma. Let me check it. Yes, it's the Poisson integral. The Poisson integral means to have this term. The potential or R2. It was the formula that I wanted you to prove it once. Integral over V theta prime lambda prime divided by L3 distance and the sigma. That's the Poisson formula actually. And then the spectral form that I wrote actually is this closed. It has this closed form. And the derivative of this function with respect to R is, I will write R over. Let me write it like a function, another function. This will be the derivative of this kernel. And I write V prime, it means that the computation points. So, now simply I remove the effect of the computation point. It's V or VB. I will remove computation point effect like this. I will say that this kernel will be V prime minus VP. VP is computation point plus remove and restore R4 pi Vp d sigma. So in this case, I come to this VR. The first integral remains the same, r psi v prime minus vp d sigma, plus the second integral. If I put this spectral form of the Poisson kernel, Poisson integral, which is actually, I will write it like this, plus plus of Poisson kernel. I wrote the formula already for you. 2m summation 2n plus 1 r over r n plus 1 pn cosine. But since the computation point is just one point, it is not. We do not need to take the integration of it. It can come directly outside the sigma. If I take this integral, simply, I will come to this formula. In this part, I have simplified. So R2n plus 1 is there, the summation, and Pn is good. This will be 2 by 2. This will be R, V, P, and this integral. If I solve this integral, and we say integral of this Pn cosine psi is equal to 2 sigma delta chronic 2n plus 1. So 2n plus 1 with this 2n plus 1, and this 2 by this 2, we have an integration over alpha, then it will be r, vp, and we will just have r over r plus 1. So that's the contribution of the computation point. And similarly, we can do it for the gravity anomaly. It's a very similar way. If you remember, for gravity anomaly, delta G was 1 over 4 pi integral of summation to n plus 1 r n plus 2 pn cosinus psi sine psi, and then we have remove and restore delta G minus delta G at computation point. So the first part remains, then I should restore it. And the restore will be delta Gp outside, and then I will have the 1 over 4 pi integral 0 to 2p 2 pi 0 up to pi summation to n plus 1 r over n plus 2 pn cosine sine d alpha. So d alpha, this term will be simplified similar to 4 pi, it will vanish with this one, and 2 pi, and delta Gp will be r over 2. So this equation can be simply written as delta G is 1 over 4 pi summation to m plus 1 r over m plus 2 pn cosine dg minus dc gp plus r over r2 delta gp. So this delta gp is actually the point exactly under the computation point. So if you have the boundary and we have point P here, this delta GP here is here. Delta G star P is here. So it's not exactly at the same point. So by this method, you can iteratively compute the downward continued gravity. So therefore I would write that delta GP at the surface will be so it is almost when you multiply this to delta G, it is almost the upward continued gravity. It's some approximation for the upward continuation of the gravity anomaly actually. I want to see it more precisely. Yep. I can write it like that. This will be this R over R 2 delta G star equals to this formula. OPN. So how do we solve that? Okay, in an iterative manner. So we write it like this. I say that okay, at the first approximation, I assume that this delta GP star, the first side, equals to delta GP that I have. So if by this assumption, I will put delta GP here, in both cases, then I get a new delta G. I will say I plus 1. This is the repetition. Then R over R2 delta GP star I. That's P star down. And just plus this integral So what's happening here? You put the first approximation delta G at the surface here, in both cases. You compute this, and you come to the new delta GP. And this new delta GP comes back to this solution again, and again you compute the new one. You repeat this until you come to that. This method is called iterative method. And there is another method which we use, that gravity anomaly at the surface is 1 over 4 pi. I write this Poisson integral like this, PR, Poisson formula, whatever it is, the kernel function. And here I have delta G star down at this. So that means that I have 1 point here, and I have here is the area of delta G star for all points here. And what I have is gravity up. But for I can discretize this formula in that way. I can write that it is summation of it. It means that this gravity anomaly at the first point, maybe here, is the summation of the kernel values to all gravity anomalies down. It is in fact an observation equation. It's an observation equation. So what is the meaning of integral? Integral is a summation. So it means that the gravity anomaly outside is summation of the gravity anomalies, all gravity multiplied by the kernel between this function as this, like this, and this summation with the unknown parameters, which are delta G down, will give you an equation. So you have one equation and many unknowns. Then you cannot solve it. Then you have another, you need to have another gravity point. Then from here, from this point, you will write again kernels between this point and all the gravity anomalies down the boundary. You will have the second equation. Then you have another delta G, P3, and you have new set of equations. So you will continue this until the number of the measurements up here over this area are at least equal to number of unknowns, and then you can solve a system of equations. So in a least square form, for example, then solution will be A transpose A inverse A transpose L. That's all. This type of integrals is called integral formula of integral equation of Fredholm type 1. Integral equation of Fredholm type 1. You can solve this. However, normally this matrix is not well conditioned. It means that the determinant of this matrix will be too small. It's not zero, because if it is zero, it is singular. It is singular, but it is something close to zero. Let me explain it in another way. I think you all know that if I have a matrix A, the inverse of the matrix will be a joint matrix of A divided by determinant of A. So if determinant of A is 0, then A is singular. So why it is singular? Well, because it will be 0 in denominator, so you cannot have inverse for A. It will be singular. However, if determinant of A is very small, this A will be ill-conditioned. So if it is not close to, it's not 0, it is something like that. So this small number will be placed in the denominator, and it causes that the whole result will be big, too big. The smaller it is, the larger it is. It means that if you have such a system and you solve it with a regular matrix like that, a Cayley matrix, Cayley inverse, then your solution will be amplified. You have very high amplification in the solution. And definitely, if you have noise in the solution, the noise will be amplified too. Therefore, for solving integral equations, you need to somehow use regularization. You need to control or stabilize this solution. You do not let this amplification be too big, become too big. You try to control it. This control is called regularization. And there are a lot of discussion, lots of things about this regularization that we can find. It's not in the subject of this course, but there are many things you can simply search on the Google. And of course, you can use collocation again. And you have delta G down, and you have delta G up. So delta G down will be, you write covariance matrix between delta G down and delta G up, multiplied by autocovariance matrix of a delta G up that you have up, and multiplied by the delta G up that you have. Then you can use least square collocation for downward continuation. So downward continuation again means to bring the data from outside the Earth to the boundary, which is actually the sphere. So different methods we have the square collocation, integral equations, iteration and the gradients approach using Taylor experiment. You can use all these three methods, all of them or any of them to use. Of course, the quality of the methods will be different. For example, this is square collocation. When you want to invert this matrix, is when the data is dense. This matrix will be conditioned as well. The numbers inside this covariance model will be close to each other, and the inversion will be a little bit problematic for that. So this square collocation has some numerical issues that you have to handle if you want to use it. If you want to use the Fredholm integral of the first kind, you want to use that one, invert that, then you need to apply some form of some sort of regularization for stabilizing the solution, because this will be high frequency will be drastically amplified and destroy the solution. You have to control them.